Right, so good morning, everyone. Welcome to the Center for Theoretical and Computational Physics weekly seminar. And today it is a pleasure to welcome Mark Miller from the University of Durham in the UK. Mark did both his first degree and his PhD at the University of Cambridge. He then moved to the University of Washington in Seattle for a postdoc. This was followed by another postdoc at the Institute for Atomic and Molecular Physics in Amsterdam, the Netherlands, before coming back to Cambridge, first as a research fellow and then as a university lecturer. And finally, in 2013, Mark moved to Durham as an associate professor, where he still is. And today he's very kindly agreed to tell us about his research on colloids on curved surfaces. So before I hand over to Mark for the truly interesting stuff, just a couple of announcements from me. First, this seminar is being recorded, so by staying on, you're giving consent to your image and voice being recorded and stored. Second, in the interests of internet stability, can I please ask all of you, except the speaker, of course, to mute your microphone and switch off your camera during the seminar. If you wish to ask a question, which you're free to do at any time, you are, of course, free to unmute yourself and switch on your camera if you so desire. Right, and now, without further ado, it's on to Mark for the seminar.
Great, thanks very much, Paolo, and good morning, everyone. Thank you for having me for your seminar this week. I have very happy memories of my visit to Lisbon for the 9th Liquid Matter Conference, and I was horrified to discover that that's already 7 years ago, 2014. But it doesn't feel like that long, but it was an excellent meeting in a very beautiful city. So yeah, good memories. I'd like to take you through some ongoing computational work today, looking at the effect of curvature on soft matter confined to surfaces, and nominally thinking about colloids, but really treating them as a model system for probing the effects of curvature more generally. And the three topics that I've listed, nucleation, migration, and frustration, map onto three strands of the work, which I'll take you through in turn. Changing the first slide is always hard, but there we go. Just to put myself on the map, I'm here at the University of Durham in the northeast of England, in a rather small but very old city, and it's dominated by this World Heritage Site. You can see the castle here, built by William the Conqueror to control the north of England. That's part of the university now, and the cathedral, which was built shortly afterwards in the late 11th century. So it's a very agreeable place to work, and Paolo has already visited, and I hope that maybe some of the rest of you will have a chance at some point too. There's a lot of soft matter science going on in Durham, and I'll say a bit more about that at the end. The topic for today is in these three parts. I'm going to start off with the simplest kind of curved surface, a sphere, which has uniform curvature, and we'll be looking at the process of phase transitions, in particular from a gas-like state to a liquid-like state. I'll then move on to cases of non-uniform curvature using a torus as my exemplar. And finally, I'll give you some preliminary results for packing and the frustration of packing of colloidal particles on conical surfaces. And a lot of this is inspired by experimental work, which I'll also mention. Here are the people I've been working with. There's my colleague Halim Kusumat-Maja from the physics department in Durham. Two of the students we co-supervised, Jack Law and Finley Gerrand, who have both submitted their theses now. And Alex Wong and Jacob Dean were two project students with me in the chemistry department who contributed sufficiently to become co-authors on two of the papers. So onto the first topic, nucleation on a sphere. And there's been a lot of work on systems on spherical surfaces. The work that really got us starting to think about it was done by Vinny Manoharan at Harvard, and his group there had synthesized polystyrene spheres of a sort of micron size and absorb them onto the interface between oil and water in a water in oil droplet. And using their confocal microscopy, they could see in exquisite detail the structures that these systems form. And because of the attractive interactions between the colloidal spheres, as you might expect, they try to form a hexagonal lattice, but because of the curvature of the surface on which they're confined, that hexagonal lattice can't grow indefinitely and produces these sort of branched ribbon-like structures. There's been a lot of computational and theoretical work as well, not least the famous Thompson problem of charged particles on the surface of a sphere, his original model of an atom. The picture on the top right here is taken from work by David Wales's group in Cambridge and Paul van der Schoot's group in Eindhoven, where they looked at particles with an attractive component as well, covering the surface. And as I'm sure everybody knows, you can't tile the entire surface of a sphere purely with hexagons, no matter how distorted they are, because there's a topological constraint. The Euler characteristic of a sphere is 2. And that means that there have to be defects. And the question is, what are the defects and how do they depend on the potential of interaction between the particles and on the temperature? So entropy plays a role at finite temperature. So all these studies have really concentrated on ordered structures or defective ordered structures. We thought it would be interesting to look at the fluid phases as well. And in particular, the transition between fluid phases. And we normally think about that in terms of classical nucleation theory, where in 3 dimensions, we would assume that we've got a droplet that grows spherically. And so there would be a free energy penalty for the growth of small droplets because of the surface tension contribution to the free energy. And that will scale as the surface area, in other words, as the squared radius of the droplet. But at the same time, there's a bulk contribution which decreases the free energy as the volume, in other words, the cube of the radius. And those fight against each other, and somewhere in the middle there will be a critical size where the free energy is a maximum, and that's the nucleation barrier. And in principle, these ideas transfer to 2 dimensions as well. So you could imagine a 2-dimensional system. The equivalent assumption would be that the nucleus of liquid grows as a circular disk rather than a sphere. And then the equivalent of the surface tension would be the line tension, which would grow as the perimeter, so as r rather than r squared, and the bulk term would go as minus r squared rather than r cubed, the area of the disk. But on the surface of a sphere, we have some additional considerations. And one thing to note is that a sphere has a finite area despite having no edges. And that means that we're no longer in the thermodynamic limit that we normally consider in thermodynamics. We have a finite size. And so the ensemble matters, and it's possible to think of at least 2 physically meaningful scenarios. You could imagine a closed system where the number of particles is fixed, and then we would have to work in the canonical ensemble at a given temperature. And in that case, the equilibrium states of the system can be inhomogeneous. If the system is cool enough to condense, then we would get a sort of liquid-like droplet, but unavoidably, there would be a boundary to that droplet, and that comes along with a line tension penalty. But what we would see, what we would expect to see, is the equilibrium between a liquid-like droplet and a depleted gas, a sort of bald patch on the other side of the sphere. The other scenario that we could imagine is an open system where the spherical droplet is sitting in a bath that can exchange not only heat, but matter as well. And then the number of particles would not be fixed on the surface. Instead, we would fix the chemical potential and we'd be working in the ground canonical ensemble. And in that case, we wouldn't expect to see stable states where there's a boundary, as in the canonical case, because the system can always remove the boundary by either taking out lots of particles to get to a gas or putting in more particles to cover the surface entirely with a liquid. And by the way, all my snapshots are color-coded by the number of neighbors of each particle, just based on a simple cutoff criterion. So we'll look at both these cases in turn, starting off with the open ground canonical case. The first thing to check is the phase diagram, and we're just going to use the good old Lennard-Jones potential as our test case. Most of the results I'll show you today are for a spherical surface of radius capital R, which will be a multiple of 7 of the particle size as measured by the equilibrium pair separation of the Lennard-Jones potential. And that's big enough to see the effects, well, big enough to get a decent number of particles on, a few hundred particles, but small enough to see the effects of the curvature. Well, in the grand canonical ensemble, we can get the phase diagram just by doing a simulation and monitoring the histogram of the density, which will be bimodal below the critical point, and we'll see a low density peak corresponding to a gas-like state, and here is the density of that state, and a peak corresponding to the liquid-like state here. We repeated the calculations on a planar surface with the same area as our sphere, but with periodic boundary conditions, so that, again, we don't have hard boundaries and we have the same area. And what you can see is there's basically no difference. The planar case, the orange dots, and the spherical case, the blue dots, basically have the same coexistence densities. And that's not too surprising because there's no strain to speak of in a fluid phase. There are finite size effects, but those are apparently very comparable because we've given our planar and spherical system the same area. So the next thing we need to do is really to find out how we can get from the gas-like state to the liquid-like state. And we want to track that free energy profile that I sketched in the previous slide. We can do that in a grand canonical simulation by counting the concentration of clusters. For small enough clusters, there will be natural fluctuations that happen on a quick enough timescale that we can just do a Monte Carlo simulation and count clusters. But to get the barrier, we really need to bias the system towards that region, which is unstable. And we do that using umbrella sampling, basically forcing the system to explore a narrow range of cluster sizes around a given target by this harmonic potential. And then we just shift the bias along the n-axis until we've got the whole profile. And what I'm showing you here are the contributions from the different windows in different colors that have been stitched together to make one coherent profile. And indeed, there is a state halfway along where there is this sort of spherical cap-like nucleus. But of course, because of the finite size of the spherical surface, the free energy can't just keep decreasing as it would normally in classical nucleation theory and in a bulk system. There comes a point where the surface is full, and then actually the free energy will go up if we put more particles on. So what we'd like to do is come up with a modified version of classical nucleation theory that captures this. And this is how we do it. We imagine taking our sphere covered in the gas-like state and consider removing a patch of gas, which we will treat as an ideal gas. And we will replace that patch with a liquid-like nucleus. And we will treat that at the van der Waals level of a fluid. So it will have a parameter to account for the attraction between the particles, the A parameter, and a parameter to account for the excluded volume, B. We will make the simplest assumption that the cap grows in a spherical way, like this sketch on the right, which is the equivalent of the classical nucleation theory assumption on a sphere, which would be a circular disk. We don't need to make any assumptions about the area of the spherical cap. We can optimize our free energy for a given number of particles to get the area naturally. So we don't have to make any assumptions about density. So if you take that approach, the formula that comes out is this rather lengthy thing here for the grand free energy change for the formation of a cluster of n particles. And all these terms have a physical interpretation. The first three of them are the grand free energy of the droplet. And hopefully you can make out that this first term is a sort of entropy term. It's a bit like the Sacco-Tetrode equation in 2 dimensions. And this is where the van der Waals B parameter comes in. We want to take account of the fact that the more particles there are in the droplet, the less space there is for the translational entropy. So that's subtracted from the area of the droplet here in the logarithm. The next term is the attraction from the between the particles as modeled by the van der Waals A parameter. And the final term here is the effectively the Gibbs energy of the liquid in terms of the chemical potential of the liquid, which I'm representing as an activity, ZL. And this activity doesn't have to be the same as the activity in the bath, because the droplet is not in equilibrium with the bath, and indeed there's a line tension. So effectively this is entropy, internal energy, Gibbs energy, and those combine in the usual way to make the contribution to the grand free energy in the grand canonical ensemble. The next contribution is the interfacial term. So there's the interfacial free energy, the gamma, the line tension. And this thing in the square root is the relationship between the area and the perimeter of a spherical cap. So this is where the geometry of the cap comes in. And then finally, really, there's the free energy of the gas that we've removed to make the liquid droplet, and then a sort of shift term that includes, amongst other things, the overall translational entropy of the droplet. So it's a bit of a long expression, but it can be understood. And there are 5 parameters to deal with here. We've got the van der Waals parameters, A and B. We've got the chemical potential inside the droplet. We've got the line tension, gamma, and this basically shift term at the end, D. And we will treat those as fitting parameters. So let's see how that model copes. Here's a measured free energy profile from the simulations, like the one I showed you before. And if we just play devil's advocate and try to fit this using classical nucleation theory on a plane, the best we can do is that. It doesn't capture the shape of the barrier very well, and of course it just keeps going. If we take into account the geometry and put in the spherical cap and basically do classical nucleation theory, we get that, which is a lot better. It gets the shape of the barrier better, but of course it still doesn't capture the increase at the end because we haven't put the finite size in. But if we do that full model that I had on the previous slide, we can get a fit that looks a bit more convincing, this blue line here. And it doesn't capture the shape of the barrier perfectly, but it's not bad. And importantly, it gets the increase in free energy at the end. And the term that ultimately gives rise to that is that first entropic term. Effectively, when you put too many particles on the surface, their own excluded volume removes or decreases the space that's available, and the translational entropy goes down, and that's unfavorable, so the free energy goes up. So we thought that was a reasonable model to capture the effects and the measured data from the simulations. You could say, of course, we had 5 free parameters to fit, so maybe it's not too surprising that we could get a decent shape. But we can go further. Here's a set of 5 free energy profiles for the same size of sphere and the same temperature, but just different chemical potentials. If you increase the chemical potential, then you favor the liquid state and the free energy barrier for nucleation comes down. And what I'm showing you with the dotted lines are the free energy profiles from the simulations. Now, to fit those, given that we've chosen the same surface and the same temperature, we really ought to have the same values of the van der Waals parameters in all cases, A and B. And also the D parameter, this cluster translational entropy term. And to be honest, also the interfacial line energy term should be the same. So gamma should be the same for all these curves. So the only thing that should really respond to the chemical potential of the bath is the chemical potential of the droplet. And so we can get these reasonable fits to all 5 of these profiles, keeping 4 of the parameters the same for all the profiles and just allowing 1 of them to vary. And so that, I think, provides a bit more sort of convincing evidence that the model has some sense to it. One of the other things that we can do with the data that we have is test a prediction that was made by this group in Nature Communications a few years ago. And what they predicted was that there should be a relationship between the size of the critical nucleus, measured as a radius, on a plane, and that's RC0, and the size of the corresponding critical nucleus on the spherical surface. And this argument is entirely geometric. It's to do with the circular disk versus a spherical cap. And you get this arctan relationship if you work it out. Well, we can test this with our simulations. Actually, without using that thermodynamic model, we just run the simulations and measure the size of the critical nucleus. And in this plot, I'm plotting basically the left and right-hand sides of that equation. Perfect agreement would be lying on this diagonal. And we've chosen a selection of different temperatures and tweaked the chemical potential to give us nucleation, and looked at a variety of different sphere sizes. And what you can see is that on the whole, yes, the points do lie on the diagonal. And so a large part of the nucleation process is accounted for by the geometry. But over here, you can see some significant deviation. And that's in the regime of a small spherical surface. So when this capital R is relatively low. And what seems to be going on there is that the greater curvature that you get on smaller surfaces, smaller spheres, is affecting the line tension parameter. And so what we did was to take all our free energy profiles for each of these cases, fit them with our thermodynamic model, and in almost all cases, the line tension parameter, gamma, that comes out is pretty consistent, which again is quite reassuring from the point of view of the model. But what we find for the smaller spherical surfaces is that the surface tension starts deviating. And that's the origin of this departure from the diagonal line. So if you do make the surface small enough, then the line tension starts being affected, and that also has an effect on nucleation. So that was the open case, the grand canonical case. Let's look at the closed case now. And as I mentioned at the beginning, we would expect to see a rather different behavior here. We would expect to see at sufficiently low temperatures condensation of the droplet onto part of the sphere, and the depletion, corresponding depletion of the remaining gas phase. And we'll eventually reach a state where they are in equilibrium with each other, but with this interface between the two. Now, this effect, of course, occurs in other systems as well. You could get basically the same effect in an ordinary three-dimensional system if the volume and number of particles are both fixed. And then you could get either a droplet or a slab, depending on boundary conditions. So in fact, a theory for this has been worked out already in the 1970s by Bruce Byrne and his collaborators. So what we decided to do was to modify that theory for the case of a spherical geometry and 2 dimensions. So the basic idea is that the condensation of the droplet will result in the depletion of the gas, and that eventually will become arrested, because to suck all the gas particles out of the gas phase would be entropically unfavorable. There's some benefit to leaving a few particles in the gas. So there's a natural point where the process stops, and the model that we modify basically treats the gas at the gas and the liquid at the second virial coefficient level of non-ideality. We can work out the second virial coefficient in the usual way, just with the 2-particle integral. We just have to account for the spherical geometry. That's easy enough to do. So we can work that out exactly, no fitting needed. And also, we've got this boundary here, the exposed edge of the cluster. The line tension for that ought to be the same, really, as from the grand canonical case. And so we don't need to fit that either. We can port it from our previous fits. And so when all this is done and dusted, there's only really one free parameter, which is a vertical offset of the free energy, basically a reference free energy. And so here are some results. This is now the Helmholtz free energy for the canonical ensemble, and the dashed lines are the simulations. So if you like, the exact free energy that's measured in the simulations. And I'm showing you curves for 4 different numbers of particles, 100, 150, 200, 250. And you can see that if we have enough particles on the surface, there will be a free energy minimum. There'll be an equilibrium cluster size, and the free energy rises in either direction. Interestingly, it rises quite sharply if the cluster gets too big, and that's for the reason that I mentioned. It's taking too many particles out of the depleted gas, and that comes along with an entropic penalty. If you don't have enough particles on the sphere in the first place, then you don't see a minimum at all. And that's because the attractive energy of forming a condensed cluster is not enough to compensate for the loss of gas phase entropy. The solid lines on this plot are the one parameter fits of that modified model by Bruce Byrne. And we were quite pleased with this agreement because there is only one parameter free in each case. And one of the ingredients to avoid fitting was the line tension that we adopted from the grand canonical simulation. So I think that provides further evidence that the models are consistent and are physically meaningful. I'd just like to contrast this case with the results for the grand canonical case, because both sets of free energy profiles involve a sharp increase in the free energy beyond some equilibrium size. But the origin of that increase is completely different in the two cases. In the canonical case, it occurs at different locations, of course, because of the fixed number of particles, and it arises because of the depletion of the gas phase, the removal of the gas phase entropy. Whereas in the grand canonical case, these are the results I showed you before, the increase always occurs at the same location, and it's due to overcrowding of the sphere, the removal of space for accommodating more particles. So similar sort of effect broadly, but for very different reasons. So here's a quick summary of the work on a sphere. We've got this interesting case of a finite space that has no edges. In the open grand canonical case, we see a nucleation process. In the closed canonical case, we don't really see nucleation. It's more like arrested spinodal decomposition, really, but there's an equilibrium cluster size if there are enough particles on the sphere. We've produced modified thermodynamic models for both cases. I should say, I didn't show you the formula for the canonical case, and that's because it's hideous. It really is very long, and it's not so easy to pick apart with a physical interpretation once you've tidied up the algebra. But you can see this paper if you're interested in the derivation. But then the satisfying thing is, yes, we can transfer the chemical. The line tension parameter from the grand canonical case to the canonical case, and everything still makes sense, which we found very reassuring. And all this was written up for the birthday edition of Molecular Physics for Dan Frenkel's 70th in 2018. So all the details are there. Let me move on to the case of non-uniform curvature using the torus as my example. First of all, let me just recap how curvature or non-uniform curvature can be described. There are a couple of ways. If you have a curved surface and you pick a point on it and you draw a normal through the surface at that point, you can put a plane that intersects the surface that contains the normal, and work out a radius of curvature for that intersection by the radius of the circle that most snugly fits the intersection. The inverse of that is the curvature. Now, if you imagine rotating that plane, the curvature will change, and you can locate the maximum and minimum curvatures. The product of the maximum and minimum curvature is the Gaussian curvature, and the average of the maximum and minimum is the mean curvature. Now you can also attach a sign to the curvature of the intersection by whether the circle that you draw is on one side of the surface or the other. So the Gaussian curvature has two possible signs. It can be positive for a surface like this, or it can be negative for a saddle like this, because you can see that the curvature is different in the two directions. It can also be zero, even for a curved surface. A cylinder has zero Gaussian curvature because in one direction, the intersection is just a straight line. But the mean curvature for a cylinder is non-zero. Anything with a zero Gaussian curvature can be unrolled without distortion onto a flat net, but that can't be done if the Gaussian curvature is non-zero. Okay, so with that said, the motivation for studying non-uniform curvature partly comes from biological applications. For example, cell membranes, where macromolecules can sometimes express a preference for regions of different curvature, usually on the basis of their shape. So for example, if you have a protein or something with a wedge-like shape, that will fit most snugly in a lipid membrane that has a particular Gaussian curvature. Similarly, there are proteins that can attach to the outside of a membrane. These bar protein complexes are sort of banana-shaped, and if the second derivative of the banana matches the curvature of the membrane, then you get a more acceptable fit and stronger binding. But we're going to go back to our model of simple spherical particles, which don't by themselves have a preference for a particular type of curvature, at least not in our model. And I've chosen a torus as my exemplar of a non-uniformly curved surface because it has regions of positive Gaussian curvature, these red bits on the outside, negative Gaussian curvature, the green bits on the inside, and of course, at least a line of zero curvature on the top and the bottom. Just to be coherent, I'll present most results for a particular torus where the major radius is 7 times the equilibrium pair separation and the minor radius is 5 times it. And we'll stick to 300 particles on the whole, which is only enough to cover part of the surface. And we'll want to test the effect of the range of the potential. So I'm going to use a potential that has an adjustable range parameter, the Morse potential, and that, just to remind people how that works, a small value of rho corresponds to a long range potential and a relatively soft repulsion, so like this red curve here, whereas a large value of rho is the opposite, a short range stiff potential. So large rho, short range. And I should mention that the interaction works through the surface, not along the geodesics. I won't go into the technical details of the calculations, but suffice it to say that they are non-standard calculations, and there are no sort of off-the-shelf programs that you can use for this. For the thermodynamics, we use a Monte Carlo simulation where we have to take account of the fact that we're working in curvilinear coordinates, and therefore we have to put the metric tensor into the acceptance criterion for the trial moves to get the correct statistics. We'll do some molecular dynamics as well, and you can do molecular dynamics on of particles constrained to curved surfaces using a method developed by Stefan Paquet and others. It's basically a single body, a one-body version of the Rattle algorithm. So I'll show you one result from that. We'll also want to look at low energy structures. So we'll be looking for the global potential energy minima, and we'll do that using the basin hopping algorithm that was popularized by David Wales. And that is basically a Monte Carlo simulation with one twist. After each trial move, you perform a local minimization, and in the acceptance criterion for the move, instead of using the actual energy, you use the minimized energy. And what that effectively does is to transform the potential energy surface, this wiggly black line, onto a series of plateaus, because all points within the basin of attraction of a given minimum are mapped onto the energy of that minimum. And that effectively removes the barriers between adjacent minima and makes it easier to explore the surface. And then for good measure, we throw in some parallel tempering as well. The first thing we can do is to see what sort of states we get for our system as a function of the temperature, the dimensionless temperature on the vertical axis on this phase diagram, and the range of the potential rho. So long range on the left, short range on the right. And as you might expect, for sufficiently high temperature, we see a gas-like state covering the entire surface. Again, the particles are colored by their coordination number. If we cool the system down, then it will try to crystallize and form a hexagonal lattice, but that will be distorted due to the curvature. And therefore, the system will generally seek to be in regions of low Gaussian curvature when it's forming a crystal. And so we label that state as X0, X for crystal and 0 for the flat regions of the torus. There's also a liquid-like state, as we might expect, for sufficiently long-ranged potentials. And as in 3 dimensions, the liquid state gets squeezed out for short-range interactions. But the liquid prefers to be in the hole of the donut. Yeah, so we call that an L- phase because it's in the region of negative Gaussian curvature. And then to our surprise, there was an additional state on top of the gas, liquid, and crystal, which was a condensed state, but on the outside of the torus, in the region of positive Gaussian curvature. So we've called this C+. And that exists at cooler temperatures. And the order in the state varies actually within the state. We can measure the degree of crystallinity using the Steinhardt order parameters, just projecting onto the torus. And what I've done is to color the symbols here by the extent of the crystallinity on this blue scale on the right. So there are some interesting things going on here. First of all, we see a coupling of the phase of matter to a location on the surface. That needs explaining. And we also see another stable state in addition to the 3 that we would expect that's stabilized. And so we have to show that that is indeed a distinct thermodynamic state, and we have to explain why it arises. And the implication of this phase diagram with the coupling of the phase and the location is that if we were on the boundaries and the system were sort of going from one state to another, the cluster would have to migrate on the surface to its new location. And that's unusual. Normally we think of phase transitions as occurring pretty much anywhere because space is, 3-dimensional space is the same everywhere. So all of this can be explained in terms of 3 competing effects. The first one is the perimeter of the cluster. There's this unfavorable exposed edge, but the length of the edge depends on where it is on the surface, where the cluster is. If we take a patch on the outside of the torus in the region of positive Gaussian curvature and constrain its area and optimize its shape to have the minimum perimeter, we find that the perimeter grows with area like this, this solid red line here. If we do the same process in the region of negative curvature in the middle, we find that the perimeter is considerably larger for a given area. And so to minimize the line tension, this perimeter effect will drive the cluster to regions of positive Gaussian curvature. Then, of course, there is a strain effect. If the system is trying to form a regular hexagonal lattice, then it's going to want to be in a region of low Gaussian curvature in order to avoid being distorted. Now, for sufficiently long-range soft potentials, it can withstand the curvature. So here is the global potential energy minimum for a particular number of particles. The blue particles have 6 neighbors, but you can see very clearly some defects here, which relieve the strain. Incidentally, on a torus, there is no topological requirement to have defects. The Euler characteristic of a torus is 0, but they arise because of the strain. Now, if I change the color scheme to show you the strain, in other words, the deviation from the optimal pair separation of particles, you can see, as expected, there is a lot of strain around the defects, but there's also strain away from them. And although this looks quite regular, it is, of course, distorted. And that comes along with a penalty. And therefore, this effect will depend on the range of the potential. So here's another long-range case. But if we go to a short-range potential, a larger value of the Morse rho parameter, then a small amount of distortion comes along with a high energetic penalty, and the system will therefore prefer to be in a region of low curvature, which minimizes the strain, even if that comes at the expense of generating a large perimeter. So this strain effect drives the system towards regions of zero Gaussian curvature. And then the final effect is to do with local packing, even in disordered states. On a plane, you can fit 6 particles neatly around any given particle, and they will all be content. But on a curved surface, that's no longer the case. And in particular, if you look at a region of negative Gaussian curvature, as we've seen, the perimeter increases more rapidly with area. And so you can fit 6 particles round any given particle and still have a bit of space left over. And that allows non-neighbours to approach slightly more closely. And if the range of the attraction is sufficiently long, that comes along with a stabilisation. And so what we did to quantify this was to perform a grand canonical simulation of a liquid covering the entire surface and look at the average energy of particles as a function of their so-called colloidal angle, this angle measuring how far from the outside to the inside of the torus we are. And you can see that that average energy drops by a notable amount as we go from the outside to the inside. And so there is a stabilization that comes with negative Gaussian curvature. So we've got 3 effects: perimeter, strain, and non-neighbor interactions that favor respectively positive, 0, and negative Gaussian curvature. Those effects fight against each other and come to various compromises that result in the 4 states that we see. So that additional state on the outside of the torus is a compromise between minimizing the perimeter, but also not distorting the cluster too much. So if we look at the boundaries between the phases, we ought to see coexistence. And here are some free energy plots of that same system as a function of 2 order parameters. On the horizontal axis, we've got the fraction of particles lying on the outside of the torus in the region of positive Gaussian curvature. And the vertical axis in each case is the number of particles in a crystalline-like environment. And we can see all pairs of coexisting states. Here is that mysterious C+ state coexisting with the liquid in the middle of the torus with a barrier between them. Similarly, the C+ state coexisting with the crystal with a barrier between them. And the implication of this, if you have a bistable free energy surface, dynamically, you would expect the system to explore each minimum for a prolonged period of time and then occasionally overcome the barrier and switch to the other state. And that's what I'm showing in these insets. The inset traces the most relevant order parameter for the transition in question as a function of time. And you can see rapid switches between the 2 states in each case. And I'll show you one example of that. Here is the equilibrium between the liquid and the C+ states, now rendered as a 3-dimensional surface. And we're going to look at this animation starting from the C+ state. So there are the particles on the outside of the torus, occasionally probing the hole of the donut, but then falling back again. And eventually it will find its way into the middle of the torus. And that is the L- liquid-like state. There it is, pausing the simulation. You can see something that looks rather like this. So it's gone over that modest free energy barrier. We could look at other surfaces, of course. We've also looked at sort of egg box-like surfaces, sinusoidal in 2 directions with periodic boundary conditions. There's a different interplay between the 3 effects there. So we only see 3 stable states, but they are coupled to location. We could look at different shaped toruses. We could look at a skinny torus. In that case, we could see a sort of wrapping state. Or we could put a different number of particles on the torus. This state has it wraps around the hole in the donut as well as the tire. But all these effects can also be explained in terms of the 3 competing effects of perimeter, strain, and nearest or non-nearest neighbor interactions. So here's a quick summary of the torus. We've seen a coupling of the state of matter to the location on the surface, and therefore migration of the cluster at phase transitions, a wholesale migration, and even the possibility of new thermodynamically stable states. And note that this is even occurring for simple spherical particles. Individual particles have no preference for any particular location, unlike the biological case, usually, where the particles have a shape that prefers a particular curvature. So this is a collective effect, and it arises from the competition of the perimeter, the strain, and the non-neighbor packing. And so all this was written up in excruciating detail in this paper that was published last year. And finally, just let me use the sort of final few minutes of my talk to show you some preliminary results for packing on cones, and the frustration that will usually arise and how that gets resolved. And this was very much inspired, again, by Vinnie Manoharan's work at Harvard. Here is a picture, which is not yet published, actually, on the right, of a glass capillary that's been drawn out into a cone, covered in micron size, roughly, colloidal particles. What they have published very recently is the equivalent of that system on cylindrical surfaces in a similar spirit. In fact, their surfaces are only nearly cylindrical. They are slightly tapered, so technically they are slightly conical. But they've looked at the formation of the crystal-like structures and the defects that arise. Now, on a cylinder, you can have unfrustrated packing, if you like, if you have an appropriate diameter for the cylinder. This sketch is again taken from Vinnie's paper. So if you imagine taking a hexagonal lattice, the red circles, and then unrolling the cylinder into its net, which would be a rectangle. Basically, what you want is for the edges that you're going to join to roll up the cylinder to be commensurate with each other. And you can get that by making sure that you can get from one edge to the other in an integer number of steps along the crystal directions in the hexagonal lattice. If you can do that, then you can roll it up without any frustration. And a similar effect arises in carbon nanotubes. You've probably seen different ways of connecting those up and getting different diameters. Now, a cone is a little bit different. It also has zero Gaussian curvature, but here's an interesting effect. If you draw a straight line on the net of the cone, which is this, this segment of a circle, then when you form the cone by connecting up the straight edges, that straight line will intersect itself. Now, because there's no Gaussian curvature, that straight line is a geodesic. So what we're saying is that the geodesics intersect themselves. And if that straight line is one of the directions in a lattice, then we're going to get a collision. Except if the angle of the cone is a particular value. If it's a multiple of 60 degrees, then the rotation or the angle of this intersection is commensurate with rotating the crystal by 60 degrees. So in other words, if I follow a direction, go off one of these straight edges, I come back on the other straight edge at a corresponding angle. And you can wrap that up into a frustration-free structure. But that only works if the angle of the cone is exactly a multiple of 60 degrees. Any deviation from that will lead to increasing frustration as you go away down the cone to larger diameters. So we're going to look at a model of that again, using Morse particles, so we can test the effect of the range of the potential. We will look at a conical segment. We're going to chop off the tip as well, because that's not even well defined experimentally. Therefore, for the first time, we need to apply a potential to constrain the particles to the surface. Otherwise, they'd fall off the edge. So we put an r to the minus 12 repulsion at the top and bottom. Because of the zero Gaussian curvature, we can unroll this onto a net and do a Voronoi analysis on the net. And I'll stick to a constant number of particles for these results, just 200 particles. So what if we torture the system and give it a net angle that is as far away from a multiple of 60 degrees as possible? So let's say 30 degrees, right? Well, then of course, there is no way to match up the crystal as it hits itself coming round the torus. And I should say this is basically ground state structures obtained with basin hopping again. And basically the direction of the crystal here is just incompatible when it comes around the other side. And so we see this scar running down the middle. Now I have to apologize, my color scheme has changed here. The green particles are now the happy ones with 6 neighbors, and the blue ones have 7 neighbors, the red ones have 5 neighbors. The yellow ones have 6 neighbors, but the Voronoi hexagon is heavily distorted, and that's quite useful for picking up distortion in the packing. So here is the 3-dimensional rendering of that structure. You can see the sort of scar of alternating 5- and 7-fold particles flanked by distorted 6-fold particles. What if we, instead of torturing the system, we just tease it slightly and take an angle that is only slightly different from one of the optimal ones, so 70 degrees rather than 60? There'll be some strain to deal with here, and then the solution depends on the range of the potential. For a long range, a relatively easygoing potential, soft, it can spread the strain out across the whole structure, a bit like it did on the torus, possibly forming a small localized defect. For a short range potential, like the colloidal case, this is unfavorable because a small distortion comes along with a large energetic penalty, and so it will tend to have an optimal spacing for most of the cluster, but then all the frustration is concentrated into a sort of mess down the middle. But I think the really interesting cases are the very narrow cones, a bit like the experimental case, where the widening happens very gradually. I've rotated the nets now to fit on the screen more conveniently, but here is a case where a wedge opens up. Basically, the widening of the cone is just pulling the planes, or the lines of the crystal apart until a gap is large enough to insert a new row. And here are the first few particles of a new row. That, I think, does have an equivalent in 3-dimensional crystals. It's the equivalent of an edge defect, where you can get a half plane starting somewhere in the middle of the crystal. Just taking that down to 2 dimensions, you get a half line, if you like. But here's a defect that doesn't have a 3-dimensional equivalent as far as we know. Now, remember that there are boundary conditions, periodic boundary conditions. This top straight edge will roll up to meet this bottom straight edge. And what we're seeing is a sort of helix of distorted particles that wraps around the cluster. Here's the 3-dimensional rendering of it. And what's happened is we've got 2 rows where the number of particles in the 2 rows differs by 1, but that additional space has been spread out evenly. So we start off with regular hexagons here. They become more and more distorted. We eventually reach a point where a 5-fold and a 7-fold particle are opposite each other, and then out the other side. And that relieves the strain in an interesting way. If we look at the direction of the lattice, upstream of the defect, if you like, and then downstream, the crystal has been rotated. Those 2 lines are not quite parallel. And that rotation allows for a slightly more commensurate meeting of the crystal as it comes round the azimuthal angle of the cone. And so, as I say, I don't think there is a 3-dimensional equivalent of that. So we still have some explanation to do. So here's a quick summary of the cone work. We see frustration in the packing in pretty much all cases, except very specific cone angles. We see these interesting wedge-shaped and helical defects, which are also seen in the experiments, by the way. We find that the solution to the frustration depends on the range of the potential, but there's still lots more to do. We've only been looking at the ground state structures, which in all probability are not what they see in the experiments. We haven't looked at the dynamics. We haven't looked at finite temperature, so all that remains to be done, but these preliminary results have been written up in this book chapter, which is now in press, in a collection of articles that's been written in tribute to our colleague Roy Johnston from the University of Birmingham, who very, very tragically died 2 years ago in his mid-50s from cancer. And this book is a tribute from his friends and colleagues to his work and his wonderful life. And so that should be appearing soon. Let me just end with a couple of slides about opportunities at Durham. As I said, there's a lot of soft matter going on at Durham. We have a centre, a virtual centre for soft matter covering 6 departments and covering a whole range of theoretical, computational and experimental soft matter. And we also have a doctoral training centre in soft matter, which very much has an industrial slant to it. So it covers everything from the sort of physics of polymer rheology to actually formulation in commercial products. It's a joint centre with Leeds and Edinburgh, and we will very soon be opening our recruitment for our 9th cohort of students. So there'll be 16 PhD positions available. There's a 6-month training process of all aspects of soft matter before the research project starts. And also, Durham is currently hosting the CCP5 Simulation Summer School. This is the school that was originally started by Mike Allen and Dominic Tildersley. Mike is still lecturing on the course, there you can see him. And so we have very distinguished and accomplished teachers and speakers. And here we are from the 2019 school outside Durham Castle. The school had to be cancelled in 2020 and we ran it online in 2021. But we're very much hoping and reasonably confident we can run it in person in Durham in 2022, and those are the dates. Bookings will open very shortly, so if you have students who might like to come along to that, look out for that. But I'll stop there, and thank you very much for listening. I'll have...
Okay, thanks very much, Mark, for a truly exciting talk and for finishing with this remarkable photo of Durham. Okay, the seminar is now open for questions. Who wants to ask questions? Who wants to ask a question? Please raise the little yellow hand, well, yellow or blue, depending on what version of Zoom you have, and ask your question. So who wants to ask a question? Come on, this is your chance. Come on. Come on, guys. Oh, I see a question there. Margarita.
Oh, hello, Mark.
Hello.
How are you?
All right, thanks. Yes.
You could be at university, are you? No.
I'm actually at home because I didn't want somebody to knock on my door, but I would normally be in, yes. Yeah.
Okay, I have a question on your interfacial tension dependence on curvature, right at the beginning for the sphere. You said
Yes.
there were some departures for
Yes.
the spheres, and you didn't say anything about it. Is it because it's just boring Tolman-like, or is it something else, or you just don't know?
Oh gosh, yeah, we haven't tried to quantify that the Tolman length. We measured the value that comes out, and basically what we found was that provided that the surface is sufficiently large, basically it stays the same. But yeah, I mean, I suppose when the sphere gets very small, what comes into play, that the packing will be slightly different. A bit like I suppose the effects that I described for the Taurus, that the non-nearest neighbor interactions will be different, and that will affect the structure and the energy of the interface. But
the Tolman thing is purely macroscopic. It's just that if the line becomes too curved, there should be something else to the tension that comes from the curvature.
I
mean, there are curvature corrections. I mean, this.
Yes, yeah, absolutely, yeah. That's right. So I suppose, I mean, the other terms in the free energy model will certainly also depend on curvature. Yes. I suppose the value of gamma that comes out is part of the package. Yes, for sure. Yes.
Okay. Thank you.
Okay, thank you. Who else has a question? More questions, please. Well, maybe I can ask a question. Mark, this is a question of a more technical nature. How do you stick your particles to the sphere or the torus? Is it a hard bond or some soft attractive potential? How do you do it?
It is actually, so we work in the sort of natural coordinate system for the surface in question. So for example, for the torus, if I go back to my, will it let me go back? If I go back to the torus, the curvilinear coordinates on a torus are the so-called colloidal and toroidal angles. Where can I show you? Well, okay, there's an angle going round this way, and there's an angle sort of going around the tire.
Yeah.
And if you work in obviously just two coordinates, then your particles can't leave the surface.
Oh,
and the problem then is that you have to account for that when you're doing the simulations, because uniform steps in those curvilinear coordinates would not produce the correct statistics. But you can account for that effectively, looking at how the area of these little boxes changes with position on the surface. Put that into the acceptance criterion, and within reason, it doesn't mess up the simulation too badly. A sphere is a sort of pathological example of that, because all the points meet at the top, right? So in that case, we still use the curvilinear coordinates, but instead of taking steps in theta and phi, we had this little algorithm where we displaced a particle onto a sphere surrounding its original position, and then project back onto the surface.
Okay.
And that has the advantage of obeying detailed balance, which actually that wouldn't work on sports. But with form steps always in different parts of the sphere. So it's actually a really good question, because we had to mess around with that to get it to work efficiently in the different surfaces. Yeah.
Okay, very good, thank you. More questions, comments, suggestions, praise, criticism? No one. Okay, well, apparently there's no more questions, so I'll just make, well, this is not actually a question, it's more of a comment, because your work on particles on the torus, it bears some resemblance with some work did by one of my collaborators, whom I invited to attend this seminar, but well, he couldn't because of a schedule clash, but he hopes to be able to watch the recording later. That's Simon Cox at the University of Aberystwyth. And what he did was simulate not a colloid, but a foam, a liquid foam, also on a torus. And then, of course, if you have a foam on a plane, it wants to be six-fold coordinated. But if you put it on various curved surfaces, then you get defects.
Yes.
Meaning vertices where, well, bubbles with the wrong number of sides. Yes. And they're not all six-sided, and sometimes you get a few five-sided and a few seven-sided ones, and you also get defects, and they tend to migrate around the place.
And is that effectively I suppose a pseudo two dimensions, is it? Because there must be a thickness to the foam.
Yes, it's pseudo two dimensional. Of course, a real foam would be three-dimensional, but this is a pseudo two dimensional.
I'm very keen to find yes, other applications of the cases. I mean, we've discovered some of them as we went along. There's some work also by Glenn McHale in Edinburgh, where they've managed to stabilize a liquid toroidal droplet.
Oh, right.
And we're talking to Glenn to see whether he might be able to put particles on them. And there are a couple of experimental scenarios where you could imagine this could be done. The difficulty normally, of course, is that toroidal droplets are unstable, and there's a huge literature on how they break apart, but relatively little on what you could do if they're stable.
Right. One other issue is your results for the torus. They were all for the same torus, right? You changed the potential range and the density, but the torus itself did not. Right. If your torus gets tighter or wider, then maybe a few things would change.
Yes, I did I briefly flashed up, ever so briefly, an example of a different shaped torus. But yes, we did look at that, and it was buried in the SI of the paper. But we did take a look at that, and things change a bit, but can still be explained in terms of the same competing effects. Yeah.
Right. Very good then. Thank you. One final look. Well, there seem to be no more questions, so let's thank our speaker again. Mark, thanks very much for a truly exciting talk and for all these stunning photos of Durham, which I hope people will be encouraged to visit. It's well worth a visit. And well, if you're there, pay a call to the venerable Bede, who lives in that cathedral that Mark so proudly displayed. I'm sure he will be happy to see you.
Yes.
Okay, Mark, thanks
and
very
thank you,
much.
Paolo. Thank you, everyone, for having me for this seminar.
Oh, thank you. And well, recording stops.